Hi everybody, we're going to spend the next couple days learning about something called improper integrands. Now there are two types, and today we're going to look at the first type. But before I start naming and labeling things, we're just going to do a little exploration here. And if you take a look at our integral, we are taking the integral from 1 to t of 1 over x squared dx. And we've kind of looked at this type of situation before, but let's just kind of refresh, and then we're going to look to see if we can notice some things. So we know that we need to take the antiderivative of 1 over x squared so we can use our fundamental theorem of calculus. And the antiderivative of 1 over x squared would be negative, what would that be? Negative 1 over x, yeah. Okay. And we're taking that from 1 to t. So now we know that using our fundamental theorem of calculus, we're going to put the substitute in the t. And then we are going to substitute in the 1. So we end up with negative 1 over t plus 1. Okay. Now, notice our integral had a bound that was a variable t. So we've talked about this before. We can kind of think about this as an area function, can't we? We'll just call it a of t. That is an area function. And what's great about setting it up this way? Well, you can change t to be whatever you want, and you're going to have the area by just substituting into this function. So, for example, let's put in 1. And if we substitute in 1, we get negative 1 over 1 plus 1, which is 0. And that makes sense because we're taking the integral from 1 to 1. But now let's put in something like 10. Okay, and if we substitute in 10, we'd have negative 1 over 10, so negative 1/10 plus 1, which is 9/10. So it's just an area function, right? It's pretty neat. But let's keep going. Like, where can this t go? Where does it end? Well, we can just keep going as far to the right as we want. Let's keep substituting in here. Let's say I substituted in 100. Well, that would be negative 1/100th plus 1. So that would be what? 99 100ths. Let's say we put in 1,000. Well, that'd be negative 1,000th plus 1, which would be 999 1,000th. Let's say that we put in 10,000. Well, that would just be 9,999 10,000ths. And I want you to look at what's happening with this and try to make an observation. And hopefully what your observation here is that the limit as t goes to infinity of a sub t is 1. Aren't these numbers continuing to get closer and closer to 1? They are approaching 1. As t increases, it approaches 1. So here's what I'm going to say. I am going to say, see if I have room down here. Yeah, I think I can squeeze it in. The integral from 1 to infinity of 1 over x squared dx is 1. Now, we can't substitute infinity in with the fundamental theorem of calculus, but we can substitute a variable in, and we can notice what happens as that variable goes to infinity. Okay. So think about really what this means. I'm going to graph 1 over x squared. And we are just looking at it for x's that are greater than or equal to 1. Okay. And take a look at this. Okay. We're saying the area under this curve from 1 to infinity is exactly 1. And that's kind of mind-blowing, but it's true. I mean, we just showed it was true. We took the limit as we were putting these t's in, as t goes to infinity, and it approaches 1. Even though it never actually gets to the x-axis, right? The x-axis is a horizontal asymptote. It never gets there. And we always are slightly above it. And we just get closer and closer and closer and closer and closer to that x-axis. However, that area from 1 to infinity is exactly 1. It's not an infinite area. You kind of would think it was, because there's always that little sliver that we're going to be above that x-axis. And it goes on forever that way. I mean, forever. But the area is exactly 1. That's amazing. Okay? It's really a really neat thing here. And when we talk about improper integrals, this is our first type where we look at infinite intervals, that we're taking integrals as they go to infinity. It's really, really kind of a cool thing to try to think about. Okay? So here's how we do it. Okay? This is type 1 improper integrals, and these are called infinite integrals. So we're taking the integral from a to infinity of f of x dx. And what we do is kind of like what we did last time. However, I just started with this. We're going to take the integral from a to some t of f of x dx, but then we're going to take the limit of that as t goes to infinity. Okay? So we switch out the infinity to a variable t, and then we find that definite integral with the t in it, and we take the limit of that as t goes to infinity. Okay? Now, if that limit exists, okay, we call it convergent. Okay? The last one was convergent. That limit exists. We did get an area of 1. The limit was equal to 1. However, is that going to happen for every function? No, not every function is going to converge and have that limit actually equal something. If that's the case, we call it divergent. The limit does not exist. It doesn't approach anything. That area just keeps continuing to grow and grow and grow and grow. All right? So what if, instead of going from a to infinity, like 1 to infinity, our last example, what if we wanted to go to negative infinity to some b, right? So think like negative infinity to 1. Well, just like before, we're going to change anything with the infinity to the variable t. Okay? So we're going to change it from t to b of f of x dx, and we're going to take the limit of that as t goes to infinity. Okay? Again, same thing. It could be convergent if the limit exists, or it could be divergent if the limit does not exist. Okay? And I can't remember, and I can't tell if I wrote it in there because my writing's kind of sloppy. Make sure that we're taking the limit as t goes to negative infinity. I may have missaid that. All right, last one. Well, what if we want to go to infinity on both sides? Okay, we have some function, and we want that area under the function forever on both sides, in negative infinity to infinity. Well, what we need to do here is we actually need to split this. We know how to do it if we're just going to infinity and just going to negative infinity. So what we do is we actually split this up into two different integrands. The first one, we'll take the limit as t goes to negative infinity of t to some number. I'm just going to call it c, okay, where c, well, I don't even think I need to write a note there. C could be anything, okay, of f of x dx plus the limit. So let's say our function is like this. Okay. And we pick c to be right here. So the first part is going to give us this. So we're taking the integral from t to c, which was actually as t goes to negative infinity. So then over here what we have to do is we have to take the limit as t goes to infinity from c to t, which is really going to be from c to infinity of f of x dx, and that will be the rest of it. So we just have to split it into two integrals like we saw before. All right, let's look at another example. Okay, last time we did 1 over x squared, okay, from 1 to infinity. Well, what if we want to do 1 over x from 1 to infinity? Well, we know we're going to switch this to be the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. Okay. So what is the antiderivative of 1 over x? That would be the natural log of the absolute value of x. Okay, and we're taking that from 1 to t. Substitute in our t. It's the natural log of the absolute value of t plus the natural log of the absolute value of 1. Now, with this, we're looking at t's going from 1 to infinity. So t is already positive, so I don't really need that absolute value. So I'm just going to call that the natural log of t. The natural log of 1, the absolute value of 1, which is 1. So the natural log of 1 is 0. So this is really the limit that we need to evaluate, the limit as t goes to infinity of the natural log of t. So the question is, what is that limit? Is it convergent? Is it divergent? Well, what's the graph of the natural log of t look like? Well, we know it looks something like this. And what happens as we go to infinity? This continues to increase, 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 increase. This limit, this function does not approach anything as t goes off to infinity. Okay? This does not exist. So we say this is divergent. Divergent. Okay. So we learned something really interesting here. We learn that, let's go back home here. We learned that 1 over x squared was convergent. Okay. It converged to an area of 1. Okay. However, 1 over x on that same interval is divergent. And what I mean by this is interesting is that the area under the blue curve is finite. It approaches 1. The area under the green curve is divergent. It does not approach a number. Okay? And that's really interesting because they both have the x-axis is a horizontal asymptote. And so what I would say is this blue one approaches the x-axis fast enough that it converges, where the green one does not approach it fast enough, so it diverges. Okay? This is really kind of head-spinning stuff, isn't it? This is neat. This is really things interesting to contemplate as we go to infinity with areas. So I've got less than 2 minutes left, so I think I'll wrap up this video, and our next example will be in the following video.